I'm Chris. I am, sorry, this is really weird. I can hear myself. I'm Chris. I'm a big tea nerd. I love spicy food. I've basically spent my entire career working on Erlang and Elixir systems. And yeah, if you guys want to like hang out, chat about Erlang, Elixir, Vim, Nix, anything like that, I'm your guy. So you can find me as Veray on GitHub, Discord, Slack, generally everywhere, apart from Twitter, where I'm still trying to get that name. So I'm really not a people person. And unfortunately, last year, I gave my first talk, and I actually used up all of my best material in my icebreaker to kind of like break the ice. So this might be really awkward, but I'm just going to jump right into it, I guess. So I'm currently a tech lead for a company called Vetspire, leading the data and insights team. So at Vetspire, we're trying to build and replace basically every piece of software that they use in their clinics. That's a CMS, appointment, scheduling, messaging, reminders, billing, like pretty much everything. Our mission is to try to give veterinarians their time back so that they can spend more of their day-to-day giving animals top quality care and spend less time fighting their software, which is, just what they do. So fun fact, the original name of this talk was The Story of a Function. It was probably a more accurate title, but I guess I didn't feel like it would be accepted or draw very many attendees. So we came up with the subtitle, Scaling Past Joins, Framework for Incremental Materialized Views with Ecto. And yeah, basically at a super high level, this talk walks through one of the first tickets I picked up when I joined Vetspire, back when it was a wee team of 4 engineers, and how it kind of blew up into this massive mammoth subsystem of an application that kind of powers all of our, powers a huge chunk of our revenue and just drives a lot of, it's just a very big problem that we have. So I was new at Vetspire at the time, only a few weeks in, and essentially we have here kind of like the main view that veterinarians will work in day out. So the patient chart contains a bunch of information, billing, medical histories, immunization histories, pretty much anything pertaining to a patient's care. You just can see it right here. And we actually have this panel on the side, which is kind of stuck there. And this is just information that we want to highlight to our veterinarians, like pretty much no matter what they're doing, right? They could be checking people out. They could be in the middle of an examination or surgery. But information here is generally what we deem to be like, super relevant to just, the day-to-day operations at the clinic. Very specifically, we had this panel here. It looks really simple. It's just the name of something and a due date. But this panel was basically just timing out, right? So join Vetspire, 3 weeks in, look at this, timing out query. I decide, hey, that doesn't sound too hard. Why not just like jump into it and take a look? Seems like a quick fix, 2 free story points. Everyone's been in this position. So this is what the query, is that visible to you guys? Yeah. So yeah, this is what the function ended up looking like. Yeah. So this is what the function basically looked like. Really, really simple, business as usual. All it's doing is it's looking at all of the immunizations a patient has, sorting them by their inserted at time and distincting by product ID. And like this query was timing out. So we actually have a tool at Vetspire that we built called Endo, which lets us very easily just take a look at our database tables and just check the indexes. Turns out that we were missing an index on patient ID. So we added it, and that was fine. So that worked really well, but this gave us some unforeseen consequences. Boom. So it turns out that the patient side panel and the query powering it actually powered multiple different features at Vetspire. So it powers 3 different things. So one of them is the side panel, which now works great and no one really complained about, but it was also used for the reminder subsystem. So basically, once a day, what we would do is we had an OBAN job which would try to look up every single reminder that was due within the next 30 days, and we would try sending out medical reminders to those people. Now, this was done really naively at first, so it was like totally timing out and no one noticed. When we fixed the issue, people started getting their medical reminders and people were happy, but they noticed some additional issues. So one of them here is you can see that we have 2 different entries for rabies. Now, if we remember the query that we were using, we were just doing a unique by product ID. And it was a complete oversight at the time, but it turns out that you can have multiple products all be like, you might have a 3-year rabies vaccine, a 1-year rabies vaccine, you might have rabies vaccines by multiple manufacturers. So our solution needed to be improved a little bit so that we could kind of like deduplicate by like more of like a higher level group, right? So this was pretty easy. But secondly, they also wanted more control over their medical reminders, right? So they wanted the capability to control when pivoting around the due date of a reminder when we sent out emails. So we wanted to remind patients maybe 2 months before something was due so they could make a follow-up appointment, a month before, 2 weeks before, maybe even when a reminder was overdue, just to chase them up. They wanted to be able to specify things like, oh, I want to contact clients via email, SMS, whatever. So we threw together this pretty simple UI. We created this concept of a cadence. And essentially, we updated our original query so that instead of just listing out immunizations, we could group immunizations under this thing called a protocol, right? So we have a protocol, very importantly, not the Elixir protocol. The naming is going to be kind of confusing. But you have a protocol. Protocol has many product IDs, maybe also things like only trigger these protocols for canines between the ages of X and Y, given maybe certain breeds only, whatever. And our OBAN job would kind of look at the protocols, look at the cadences, and in tandem, we would essentially get something like this. So we've got list protocols to send. You look at all of the products, and then you just do all of your filtering logic, right? So here we just look for all of the patients that fulfill the protocol's criteria, make sure that they're not deceased, where their age is correct. We look at all of the immunizations just via a left join that patient has ever had. We distinct and order by, and we select something in the shape of a protocol, right? So we've got a protocol ID, immunization ID, date, due date. Super simple. Ignore this repo all with the timeout. That is a sign of things to come. So that was protocols v1. We shipped it. People were happy. We were growing. And yeah, everything was going great. Already showed you the code. So inadvertently, when things like that happen, product requirements evolve. I'm sure everyone's been in this situation. So it turns out, and this is another thing where I had no idea, but at Vetspire, there are actually multiple ways of ordering products. So you can have a medication prescription. So like, let's say we just prescribe you a flagyl or something like that. You can get an immunization, like we currently have for rabies vaccines, or you can just have line items billed to you in an invoice. So our clinics were requesting that while the medical reminder system was working better now, and we were no longer sending out duplicate reminders, we wanted to be able to trigger reminders based on like line items being created on invoices. So let's see what happens to our query. So same basic stuff, look for all the patients. Now we're looking for all the order items, so we're doing this left join here. It's pretty similar to this left join. We now make our order by far more complex, sorting by their various dates and trying to grab order item if it exists or an immunization. Our selects are now slightly gnarlier because we've got to do this conditional logic to get the due dates. Actually, yeah, order items didn't have due dates, so we had to create this logic to kind of like derive them based on a protocol. So this became really, really gnarly. And as we can see, the timeouts doubled, which is a sign of things to come, unfortunately. So more left joins. So we now have a reminder subsystem that is correctly emailing or SMSing clients based on immunizations, line items, what have you. So we got into a place where clinicians were manually overriding patients' medical histories and billing histories because they wanted to change the date a reminder was sent, which is a big no-no. Like that shouldn't be allowed. So another ticket came in, and now I'm the co-owner of all of this in our team of 4. So we had a ticket come in, which was, I want to be able to customize when reminders go out. So we created the concept of a custom protocol, a custom patient protocol. Exactly the same as the immunizations and order items. We decided we'd just create a new Ecto schema, have like a static due date from there, and just add a new left join to our query like everything else. So here, this logic pretty much hasn't changed. but we've added another left join for the custom patient protocols. We've made our selects more complex. We've made our order by more complex, and we now have a query that runs for 8 hours. So, yeah, Jesus. So, we quickly realized that this wasn't a scalable solution at all, and we started thinking, okay, maybe it's time to like rewrite this. Now, how do we do that? So when we were kind of throwing stuff at the wall, we were just doing some investigation. We came into a concept of what a materialized view is. So at a super high level, for those that don't know, a view essentially acts like a database table, right? But the definition of a view is actually just a SQL query. Every time you query your view might be named like, I don't know, invoices, right? So imagine you have orders. Orders might have an invoice true or false field, but you want to create a view called invoices, which only includes orders where invoice is true. So you can create that, run your Ecto migrations, and you can query that just as though it was a normal table. The important thing is every time you're querying a view, it's rerunning your queries, and it doesn't actually solve the problem. But there is a concept which builds on top of this called a materialized view. So similar to a view, it is sourced with a query, but essentially it's cached in the database. So it's up to you to manually materialize it. In Postgres, I think there's a command called like refresh materialized view, which just drops the table and just essentially regenerates it from scratch. Again, that doesn't really help because we don't want to drop and rematerialize the entire thing, because then we still have a query that takes 12 hours to run, right? We've not actually changed anything. What we really want is an incrementally materialized view. Unfortunately, this is something that Postgres doesn't support. And when you go online, you have two choices. You either use a product that exists, such as like Materialized. I'm forgetting the other ones, but like there are products out there that solve this problem. Some of them are like Postgres Wire protocol compatible. But that costs money, which as a early stage startup, we did not really have. Also, you're trading infrastructure complexity for actually having control over the code, right? The second thing that you can do, which is what we did, is you can fake it. So Postgres has a feature called database triggers, where essentially every time you insert into a table, delete from a table, mutate rows in a table, you can call another function. So what we ended up doing was we wrote a bunch of SQL like this in our Ecto migrations, which basically says, like in this case, every time we insert into our protocols table, we also insert into the patient protocols, right? So these are the things that actually appear on the patient sidebar. These are the things that we actually want to send reminders for. Insert into this the result of this gnarly query, which I'm not going to show because it literally wouldn't fit on the slide. Same thing with updates and deletes. We had to do this for every single input, right? So we had to do this for order items, custom patient protocols. We had to do it for immunizations, but we also had to do it for other cases which you might not think about, right? So for example, what happens if a patient gets marked deceased, right? We want to actually drop all of the patient protocols related to that patient. Some of our protocol triggers changed based on the age of a patient, right? So as patients got older, rows in this table needed to be dynamically added or removed. This worked for a while, but one of the problems is with database triggers, and I don't know the actual terminology for this, but I've coined them as like low blast radius and high blast radius changes, right? So for example, triggers are perfectly fine if you're doing something in relation to inserting a new order item for a patient, right? Like the actual end result of that is pretty simple. It's kind of scoped to that single patient. You're either just deleting a row or adding a row. No big deal. But then you have changes where you're disabling a protocol. You're creating new protocols. Maybe you're creating a new protocol and you're adding a new product that can trigger that, right? And then boom, you suddenly have to dematerialize and rematerialize huge amounts of your materialized view. One of the problems with that is because you're now kind of like coupled to your other actions in the code base. So you're inserting an order item in a transaction. Postgres is going to try running your triggers. That times out for whatever reason, and then boom, you've got sudden failures caused that are completely unexpected to your engineers. No one actually knew that this logic existed unless they had touched the protocols engine. And yeah, we called it spooky action at a distance, similar to quantum mechanics. Don't try to understand it, it's going to blow up. So we decided that probably wasn't the right fit. That probably wasn't the right fit for us, especially when it came to those large blast radius changes. Totally fine for the low blast radius because they were controlled and understandable, but we just ultimately needed more control. So what we did is we ended up taking a bunch of learnings from this, i.e. materialized views are fast, but we want to keep them kind of like low impact. And we did some benchmarking on the original queries that we were trying to replace. Now, if we go back to the queries, which by the way are abridged, these are much simpler than they actually were originally. The bulk of the time that this query was executing, Postgres was spending computing the results of these left joins, and then trying to like order them and rank them and sort them and unique them. Postgres was spending so much memory trying to do these that even for like a small data set, like we're talking like a single clinic with maybe 1,000 animals, each patient maybe has a couple of items and immunizations, even for new clinics that are of like a relatively small size, Postgres was spending so much memory that it was constantly paging out. Whenever you're paging out, stuff is just going to hit the ground and just stop working. So because the issue was specifically with these left joins, we decided, hey, what if we just abandon the high-level database triggers where we're just trying to rematerialize the state of everything? Do we get any performance gains from just rematerializing those left joins independently, right? So what we ended up doing was we ended up creating a materialized view for the most recent custom patient protocol, right? We created a materialized view for the most recent order item, the most recent immunization, and that prevented Postgres from needing to do all of that complex deduplication logic, sorting logic, whatever. The query ended up just being able to join directly into rows from that table. Because we kind of knew the domain of what we were working on, these materialized views would have columns like org ID, patient ID, clinic ID, whatever, so that our selects were like super optimal as well. We could enforce that everything was indexed and things continued to work. So that solved one problem, that solved like the high impact stuff. You still had to like dynamically derive all of your protocols from all of these underlying tables. So that was still slow. But it was more understandable, and we stopped having outages every time someone tried updating a protocol. But we could do it slightly more efficiently. So we kept on iterating on this, and we kept on running into cases where, hey, maybe we missed a condition where a trigger should have fired, but we just didn't think of it. So we were kind of in some inconsistent state, right? So when it came to actually deriving the protocols, things went wrong. So Protocols v2 solved the issue, but we decided that we wanted to solve 3 problems. So one of those is we definitely want to do the materialized views because they were like super fast, but we actually did not want to do them with database triggers. We decided that that was just too magic, it was too surprising for engineers that weren't familiar with the system. So we were thinking, okay, can we take all of our learnings and all of our database triggers and our approach of like decomposing these really complex queries and kind of build a Elixir framework which made it very easy to define them and just kind of piece them together. And that's what we did. So we ended up calling the system Cinema, and I'll walk through some examples of it. But Cinema just introduces 2 very basic concepts. So one of these concepts is a projection. So a projection is a behavior that you implement. It's either virtual or it's backed by a materialized view. The virtual ones will skim over, but essentially, when we had our most recent order items, like that is an example of a projection. A projection defines some inputs, so maybe your inputs are actually like your order items tables or your base immunization tables. You get some kind of derivation callback, which gets a stream of data from those inputs. And it's your job to just write an Ecto query that declaratively takes that and selects something in the shape that you want to write into your table. And then the engine is responsible for streaming over your inputs and essentially, writing rows to that table. The second concept is we have something called a lens, which is where like the incrementality comes from. So your lens is very much defined by your use case. But for example, we had the use case where on a patient-by-patient basis, we wanted the list of the most recent things. On a org-wide basis, we want to recompute everything and make sure that all of the medical reminders goes out once a day. So that would just be 2 different lenses, right? One lens would just contain a patient ID. The other lens might contain a location ID or an org ID, whatever you want. And in tandem with the projections, we're essentially automatically scoping the inputs to be the minimal amount of data you need to recompute to materialize rows in your projection. So we jump into this. We can take a look. So at Vetspire, we start all of our projections with the idea of a patient. So patients don't define any inputs, but they do define an output. So outputs are plugged into subsequent projections. So here we're basically saying, hey, get all of the patients that belong to a specific org. Now, this patient's projection is then passed into, for example, this projection, which is our most recent custom patient protocols. So you can see that this defines a schema with all of the data that we need, but only the data that we need. It defines a single input patients, and then it defines its derivation callback. So you can see the first thing we do is we dematerialize. So certain Ecto schemas or certain materialized views, you explicitly want to dematerialize entirely because, for example, if you do a repo delete all from a source table, you don't necessarily have an input that would be, updatable in that table. So we end up just dropping everything in our projections that match a given lens. And then for the stream that comes from the previous inputs, we're basically saying, hey, for 2,000 patients at a time, run this query. Select this vague data shape, and we stream that into a projection materialize. So then the protocols engine will take control of this and essentially say, hey, give me 2,000 patients at a time, run this query, rate limit it, throttle it, and just execute. And as it's executing, it's going to be writing rows into this table. Now, we also have here, you can see most recent immunizations. It looks very similar. But again, we're only kind of like selecting the data that we explicitly need. And we then can continue composing these projections. So this ends up being the big bulk of the work. So for our patient sidebar, we have this product protocols projection, where we have, of course, our patient ID, immunization ID, which is optional, order item ID, which is optional, custom patient protocol ID, which is optional, and then a bunch of other state. And you can see that for the first time, this projection defines multiple inputs. So we need to run all of these projections to make sure that this projection has up-to-date data to be able to derive. And then you can see, essentially, we take these inputs one at a time based on the ordering of the inputs, and we just stream over it, right? So, and the derivations are run with the assumption that anything you write will be upserted. So essentially, we're basically saying materialize rows in this database table based on this projection, then run the exact same thing based on immunizations, replacing any rows that were already materialized from previous inputs. Then we rematerialize with order items, and then we rematerialize with whatever else. But ultimately, these are, again, just selecting the date, due date, blah, blah, blah. So on demand, if you're viewing a single patient at a time, you call this projection, you give it a lens of a single patient ID, and essentially the protocols engine knows that you need to start with patients, then just essentially compute their most recent, various dependencies, take those most recent dependencies and pass them into this. And the magic here is that what used to be a really the query complexity is pretty similar, but what used to be a query of a bunch of joins that Postgres would have to compute on the fly ends up being decomposed so that Postgres only needs to deal with the very least amount of data possible per stage. Now, for our actual reminder system, we build on top of this. So we end up having way too many protocols to still loop over. It's still way too much data. So what's important when we actually go out to send these reminders? Well, we only actually care about the protocols which are within some kind of date range of a cadence. So that gives us this outstanding protocol stage, right? So outstanding protocols only cares about our product protocols, but essentially we're saying for every cadence in the system, get the beginnings due date and the end due date that we actually care about and materialize rows in this table. And then finally, we loop over all of these, and as a side effect, we insert these rows, which then trigger, SendGrid O-band jobs or Twilio O-band jobs or whatever else. Um, so what our entire process looks like ends up, looking like this. And this is the cool thing about doing it this way, in that because our projections have to declaratively define all of their inputs and all of their outputs, we can actually build a graph of everything that needs to run to materialize a given stage. So when you use Cinema, you essentially request one of these to be run, and then dynamically at runtime, we build a DAG of all of the dependencies. We determine what stages have no interdependencies and thus can be run in parallel. And then we can pass that to an engine to essentially run that graph or that subset of the graph. So if we just do this. So we can do Cinema. So if we list all of the projections for the protocols application, you can see that these are the ones we have defined. But then if we wanted to run just product protocols, you can see that it just returns this list of stages that needs to be run with a nested list, which is what can be run in parallel. But you can also run a subset of this, or you can run the entire thing. And because this is ultimately just a list of instructions for how to do a specific computation, we actually have the concept of different engines that you can actually execute this graph with. So for the single patient use case, that doesn't deal with very much data, like that can run in real time. So you can actually pass this graph to a task async await based engine, and that essentially just immediately gives you the results. For a reminder job, on the other hand, we have a bunch of other business rules which are really important. So for example, we wanted reminders to go out at 8 a.m. local time. We wanted, like if SendGrid had a failure for whatever reason, we want jobs to retry. So we also include a Oban Pro workflow engine, which just kind of automatically takes care of all of that complexity for you. But the really cool thing is we ended up with this big architecture where you have a single kind of like query graph that you can run in pieces, and you can share between your single patient use case and your org-wide use case. Like you're using the exact same code, there's no duplication here. And just based on the engine you pass it into, you just get different runtime semantics. And you just get different guarantees. So you actually can, for example, I'll ignore this. So if you just run Cinema project, you give it a projection, you give it a lens, you get your data back. Super quick, rematerializes a bunch of tables. We've been doing some work recently to extract a bunch of Cinema out of our application just to share it with the wider community, and you can find it here. I think that's it.